So let's start. It is a calculus tutorial today, and it is about integration. And so, as you would know, integration is the reverse or opposite of differentiation. So calculus has two parts. It has differentiation and integration, and they're the opposite of each other. And there are some famous theorems that tell you that. Okay, so let's work through some problems together. I'm going to start in chapter 8, page 201. Now, I've already done some of these problems in Monday's tutorial, so I thought I could do something different today. So as usual, just enjoy the ride for the last time. And if you have questions, comments, please, like I say every week, feel free to smash that chat button. Let me know what's going on. All right, so let's have a look at this one here. Number 8, it has a H next to it, which means it's harder than the other ones. But really, when you know how to do this problem, it's not too difficult. And a really important strategy with this problem is to simply draw a picture. I think that's what they want you to do with part A. And then part B gives you a specific problem. So let's solve part A first, and then we can move on to part B. Okay, so suppose we have a continuous and increasing function on a closed and bounded interval. If these values are defined in the following way, then explain why the integral of the derivative is equal to this mess. Okay, so this is probably a hard question because it's not clear where you start, but a top tip from me, if you draw a picture, then this problem is quite straightforward and relatively easy. Okay, so let me share my screen with you, and I can go to my document camera. All right, so if I was drawing a picture, this is question 8A. Okay, if I was drawing a picture, what I would do is I would first of all get a pen that's working properly. Do I have any good pens here? This will do. All right, so imagine this is your function, the graph of your function. Okay, and let's mark A and B on the x-axis. All right, now they're going to correspond to C and D on the y-axis. Okay, and this is a continuous increasing function, so that's like your function f. Okay, now if I look here closely, this is what we want. Okay, so we want to prove or explain why. I guess they're really asking us to explain rather than prove this is true. Okay, so that's what they're asking us to prove. So you've got the inverse function, the f here, and all right. So you can see from that and from the picture that this is kind of going to be an area under a curve. This is also going to be an area. So if we look carefully at our picture, and this is like, I don't know, let's call this A1 and call this region A2, okay? So this part here is going to have area A1, right? That's going to be the area of A1. This part here, it's the area between this part of the curve and the y-axis. This part is going to correspond to A2. Okay, and now what about this funny thing here? What is BD minus AC? Well, if I make this a little clearer, there is a rectangle with base equal to B and height equal to D. So B times D, which is there, equals the area inside this rectangle. Now, what about the other part? Well, I'm glad you asked. A times C is the area of this rectangle, okay? This rectangle. So if I take the big rectangle and I subtract the area of the smaller rectangle, I get that plus that, those two areas, which is exactly what I want. Okay, so let's write something down. So from our graph, we see that the area 1 is this. And by A1, I mean the area of this thing too. Yeah. And this area plus this area equals the big box or big rectangle minus a little rectangle. Okay. So now if we just combine these these things together, we actually get this thing. We obtain that integral plus that integral equals this. So if we shift one of those to the side, I'll get this. Okay, that's it. So that wasn't too hard, right? Like on the surface, this looks crazy, but by drawing a picture and by carefully looking at the areas, it's actually pretty easy to explain why that's the case. Okay, why it's true. Now, the second part of this is like a concrete specific example. So let me just go back to the PDF and I'll go back to my document camera in a second. So here we are asked to calculate a definite integral involving sine inverse. Okay, and so this thing here would just sort of be the same thing here. And, you know, the f would be the sine function, and, you know, a would be sine inverse of a half, which is pi on 6, and b would be pi on 2. Okay, so let's use that. Use part A to solve this one. Okay, so let me go back to my document camera and we can finish off the problem. All right, so part B. All right, so from part A, I mean, you could put T, if you wanted to match it up with the T's there, you could put T here, right? Sine inverse T dt, it doesn't matter, okay? So F is going to be the sine function. C and D are going to be 1/2 and 1. So right, A is going to be pi on 6. You take the sine inverse of 1/2. And B is going to be equal to sine inverse of 1, which is pi on 2. Okay, so you can take those 4 things, put them into here with your sine function, and then you can do the problem. Okay, so B times D is going to be pi on 2 times 1 minus A times C, which is going to be 1/2 times pi on 6 times 1/2. Minus the integral from this to this of the sine function. Let me just go up a bit more. Okay, so we know where we're going now. All we've got to do is simplify this. That's going to be pi on 2 plus pi on 12, 5 pi on 12. And here we've got integrate sine to get negative cosine. Okay, so you can now put these in and you should get something like this. Just give me a second. Just want to check my answer very quickly. Yeah. No, that should be 12, 5 pi on 12. Okay. There you go. All right, so I just looked at the answers and they do say hint, draw a picture. So yeah, they sort of give you a hint in the back of the book, but you can see just by drawing a really basic picture and looking at the areas, you can come up with a good explanation on why this is true. Okay, now what is the significance for this question? Well, I'm glad you asked. Okay, what's easier to integrate, that or that? Okay, this is obviously easier to integrate. Okay, all right, Brian, how did we get A, B, C, and D? Well, D is your integral there, right? C, your limit of integration. So there's your integral. C is there and D is there. And all you got to do is find A and B. So what is sine inverse of 1? That'll give you that. And what is sine inverse of 1/2? That'll give you that. You with me, Brian? Yeah, so all we're doing is we're matching this up with this and saying, oh, C's got to be 1/2, D's got to be 1. And then to find the other two, you just take the inverse of those things. Okay, so just to repeat, what is the significance of this problem? Why is it an interesting problem? Well, this is much easier to do than this. So if you can take this integral and make it easier or simpler, then that's a good thing. That's a good thing. Okay. So definitely keep asking questions in the chat if you want me to repeat something, or you're not clear on how something works. It's the last week, so ask me anything. All right, so let me go back to these other problems. All right, what have we got? Okay. Yeah, okay. Let me see if I can find this one. All right. Okay, so let me go to 14. Now, this is sometimes a scary question because people see Riemann sums and they freak out. So my advice is don't freak out. So I'm looking at question 14 here. Okay, I'll do part A, and part B I'll leave for you to do, but I'll get you started with part A. Okay, so as you might remember, Riemann sums in the limit give you the integral of a function. Okay, the definite integral. And in this question, they want you to consider this function, 1 on x, on this interval. And they want you to set up the lower Riemann sum on this partition. And then they want you to come up with this kind of relationship. Okay, so when we talk about a partition, all it really means is that we're slicing up an interval into different bits or different grid points, if you like. Okay, so again, with this one, I think it's really important to be able to draw a picture. All right, so let me go to my document camera and we can see what this looks like. Okay, so I can go to a new page now. Okay, so our function is 1 on x, and we're in this interval. So x is between 1 and 2. Then, so consider the following slicing up of the interval. Okay, so what we have here is a set of grid points that are sort of 1 on n in thickness. Okay, so this is, your first, that this one's 2n on n, okay? And the sort of arbitrary point, if you like, is going to, so I guess I can write it out. Hang on, let me just go back here. So you can think of your grid points as sort of being x sub I, if you like, okay? So x sub naught is this, x1 is this, oh, sorry, x2 is this, right? And you keep this going. And so you can see what we're doing basically is adding in 1 on n each time, right? So the ith one would be n plus I on n. okay? And you get up to this. Okay. I is just the sort of the position along. So this is the first grid point, Zach. So this is the second. This is your I sub naught. This is your I sub 1, I sub 2, I sub 3. Yeah. So it's just like a way of keeping track of the counting. All right. So before we set up the Riemann sum, I'll do that in a minute. We've got all our grid points set up. Okay. But this is the most important one. And so, of course, the next one will be this. Okay, etc. All right. So before we get on to working out the lower Riemann sum, let's do something a little easier. Okay. Let's work with the actual integral of this thing, right? So down in the bottom of the part A in question 14, we want to come up with something like that. Now, I'll give you a hint. This is actually the lower Riemann sum, this thing here. And log 2, where do you think we get that from? Well, that's just, looks like the integral of 1 on x, doesn't it? From x equals 1 to 2. Okay, so we'll keep that in mind. And let's work with it. Okay. Oh, sorry, wrong one. Okay, so the integral of 1 on x dx, that's the natural log of x from 1 to 2. Now log of 1 is 0, so that's just log of 2. All right, so let's now work out the other part. We've got the easy part. So the lower Riemann sum is going to be calculated in the following way. Okay, so what is delta xi? Delta xi is just the width or the distance between each of the 2 points. Okay, so delta xi is just this. All right, so this, take away that, well, we know it's just 1 on n, right? Okay, and what is this xi star? Well, xi star for the lower Riemann sum is just the point in this interval where the graph has a minimum. Okay, so here we know this is a decreasing function. 1 on x is a decreasing function. So it has to achieve its minimum at the right-hand endpoint. So this will be f of xi plus 1. Delta xi is 1 on n. Okay. So what is f of xi plus 1? Well, it's 1 on this thing here. So you just flip it over. So all I've done is I've inverted this because it's 1 over that. And we multiply by this thing. Okay, so we're almost done now. I know this is not an easy question, but that will cancel. And what does this give us if we put in the values for I? it's going to be, well, for I equals 0, it's 1 on n plus 1, plus for I equals 1, 1 on n plus 2, plus 1 on n plus 3, plus da 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 da. Okay, 1 on n plus n, which is 2n. Okay, so that's a big mess. Let's go back to our PDF and see if we can make sense of this. We've already got the log 2. That was the easy part. Now we've got this sum here. And all we need to do in the lower Riemann sum that I've set up is to take the limit, because we know that the lower Riemann sum will converge to the value of the definite integral. Okay, so the last step in our problem is something like the following. So we take the limits in the above sum, the lower Riemann sum. We know that as n goes to infinity, this has to converge to that. Okay. As required. Oh my goodness. Now that is a hard problem. Okay, that is not an easy problem. So when some students see it, they freak out, right? They freak out. And they go, oh, there's too many things going on there. I don't know what's going on. You can do it. Now, Andy raises a really good question in the chat. What is the difference between the lower Riemann sum and the upper Riemann sum? Okay, great question, Andy. So, Zach, I'll get to your question in a minute. Okay, so, Andy, it's all about this xi star, okay? Now, in this function, because you wanted the lower Riemann sum, we wanted to choose xi star so that the function took on its minimum value on this interval, the minimum value, okay? For the upper Riemann sum, you want to change that around. You want to choose this thing so that it achieves its maximum value. Its maximum value on this interval, okay? And then both of them will converge to the same limit, and that will be the answer, okay? But in this case, we just asked for the lower Riemann sum. If you look at the next question, okay? So let me show you part B very quickly. I won't do it, but I'll show you how to do it. If you have a look at 14, part B, find the upper Riemann sum, okay? And so in that case, you want to choose your xi star so that f is achieving its maximum value, okay? So that's the difference between the two, Andy. Yeah. So the lower Riemann sum involves minimums and the upper Riemann sum involve maximums. Now, in the limit, doesn't really matter, okay, because they converge to the same thing. They converge to the same thing. All right. Yeah, no worries. It's a really good question, Andy, because one thing that freaks out students with this is actually being able to choose. Let me show you. Being able to choose the xi star. People go, "What's xi star?" And I can say, "Well, you choose it." And like, "What? I can choose it?" And like, "Yeah, you can, right?" But in these kind of questions, you're directed by whether you're dealing with a lower Riemann sum or an upper Riemann sum. Okay. All right. Yeah, Zach. So we just state to take the limit, and well, that's it. That's all you're asked to do, Zach. You're asked to show that that equals that, and yeah, in the limit, this converges to that. Okay. That's actually how Riemann sums work. All right. Yeah, it's not too bad. Okay. Celing, hello. Sorry, I don't quite understand the steps for finding the lower Riemann sum. Okay, so this is how the lower Riemann sum is defined. Okay, it's a sum, and in particular, in this case, because our function is a decreasing function, this xi star is chosen to be the right-hand endpoint because that's where this graph has a minimum on this interval. Okay, that's how that's how you, like the xi star for lower Riemann sums is the point where the function attains its minimum value on these kind of intervals. Okay, so is that the step? Which step are you having problems with? Is it the first step, second step, or third step? Because this is a definition, and then we've gone through and said, oh, this is going to be the right-hand endpoint. Ah, so what is this? Okay, so from here to here, Celing, is that correct? From here to here. So this is that, right? All I've done is I've taken, it's this minus this. Okay, so if you take this away from this, right? It's a good question. So this is just n plus I plus 1 over n minus n plus I over n. That's just 1 on n. Okay. All right. So this is that part which I calculated here. This, remember, our function is 1 on x. So if I want the value of the function at xi plus 1, all I'm going to do is replace x with this. Okay, now because I'm dividing, I just flip. Okay, so this is this part, and xi plus 1 equals this thing. So I've replaced x with that. Okay, and then I've just simplified. So Celine, can you see how this happens now? Because I've taken this, 1 divided by that is that. Yeah, so just, and cancel, and then you just write out the sum. All right, there's a few more questions. So I'm loving the questions. All right. All right, sounds like, yeah. So Sichuan is right. The upper sum is the maximum value on that interval of the function. Yep. Lower sum is the minimum. Yep. You got it. You are welcome. Keep those questions coming. All right. Whew. It's a long question. I think I need a little break after that, right? But so let's do something a little easier. So, oh, okay. Let's have a look at 15. Okay, question 15. Evaluate the following integrals by Inspection. What does that mean? What does inspection mean? Oh, hang on. Before I start that, Sir Ling, the function is decreasing. Yeah. Look, let me go back to my document camera for a second. Okay. The function here. It's a good question, right? This function is 1 on x. It's a decreasing function. So the minimum of that function on every interval like this has to occur at the right-hand endpoint. The minimum value of this function on an interval like this has to occur at the endpoint, the right-hand endpoint. Okay? So you just look and you go, oh, that's easy to work out. Yeah, Sichuan says as well, also, it's decreasing function. Lucas, you can probably use Maple. But yeah, I don't think they want you to use Maple in this particular question. TG has a good question. What if the function is decreasing and then increasing? Yeah, it's harder. It's harder. If you look at the questions in the course pack, let me just show you. The easiest situation is when the function is either increasing or decreasing. Okay, so let me just show. See, you can see this is a decreasing function. This is an increasing function. Okay, so don't worry about the other situations where it's either decreasing or increasing. Okay, don't worry about that too much. I don't think you'd be asked to do that because it's just too difficult. Okay. Yeah, so you could divide it up into smaller intervals where one of them's increasing, one of them's decreasing. That would be fine. That would be fine, right? Yeah, Zach. Like it's just like you'll get ones that are easy, and usually the points you want are the endpoints. Okay, so I would just concentrate on increasing functions or decreasing functions. Okay, let's get back to the PDF. Now, question 15. Evaluate the following integrals by inspection. What does inspection mean? Yeah, TG, I think you're right. Just by looking, I think you said that before, right? Yeah, you should be able to look at it and write down the answer. Yeah, yeah, yeah. Yao, Lucas, yes, absolutely. So you should be able to write down the answer for most of these. Okay, so if I was doing this problem and I was doing part A, then I would see, okay, x is half of the derivative of x squared. So I could, put a 2.5, something like that. So if I was doing this one, what I would do, if I can go to my document camera. Okay, so if I was doing 15A, yeah. Okay, well, I can see that well, this, the derivative of this is almost that. Okay, and so what I could do is go, the derivative of that is that, and I just do it like that. But actually, they say do it by inspection, right? So you really should just not write that down and just write that. Now, what have I forgotten? I've forgotten something, haven't I? Oh, yeah, plus C. Thank you, Zach. Okay. So you can always check later, right? You can do a guess and check, or you can, like start with this and go, if I differentiate this, do I get that? Okay. All right. Okay, let's go on to a different question. Let's do some integration by parts. Now, some of you will have seen integration by parts. Okay, so let me do a basic one just to remind you of how to do it, because some people see it at school and some people don't. Okay, if you've never seen it before, that's okay. That's okay, not a problem. All right, so the easiest way to explain integration by parts is it's like the product rule for integration. Okay, so it's like product rule for integrals. That's probably the easiest way that I can explain it. And it does involve some choices. Okay, so let me share my document camera, and we can, let's call this integral I x. Okay, so the integral of x times e to the 5x from x equals 0 to x equals 1. Okay, so there's a product here, and we need to make some choices. Now, in this one, I'm going to choose one part of the product to be equal to u, and the other part of the product to be equal to the derivative of another function, v dash. Now, you could say, well, how did I make that choice? Because you have to make a decision here, right? So one starting point is to make u the simplest function, like a polynomial, that when you differentiate it, it gets much simpler. Okay, so let's try it with those choices. If u is x, then u dash is going to be 1, and v is going to be the integral of that. And we're not worrying about constant of integration here, right? It's a definite integral, so we don't really need to worry about that. So integration by parts formula, IBP, it's the following, yeah? U times v dash dx it's this minus the integral of the product of the two things that you just came up with. Okay, so this is kind of like a product rule for integrals. Okay, so we've got u equal x, v dash equals that, u dash equals 1, and v equals that. So let's put it together. So x times e to the 5x dx All right, that's going to be the product of u with v. So that's going to be x over 5 times e to the 5x minus the integral of the product of the two functions you calculated. That's a dx hiding in there, okay? It's very small. Okay, so let's work this out. That's going to be 1/5 e to the 5 minus 0, okay? Minus this final integral. Now, this integral is easy to calculate. It's going to be something like 1 on 25 e to the 5x. Okay, so let's simplify this part and then we're done. So e to the 0 is just 1. Okay, so let's simplify this now. So that's going to be 5 on 25. So we're going to get something like this. So minus minus will give you a plus. Okay. Now, what happens, who can tell me in the chat, if you know, what happens if I switch the choices around? What happens if I let u equal that and v dash equal that? Can anyone tell what's going to happen? Will I get the same answer? Who can tell me on the chat? Anyone? Who can tell me? If I switch the choices, if I let u equal that and v dash equal that, would I get the same answer? So some people are saying yes. Some people are saying, well, we actually cause a worse problem, a more difficult problem. So yeah, in general, the choice here is very important. Okay, yeah, you will get there is a strategy involved with making these choices. So you can't just always switch them and you'll get the same answer. Sometimes you can get more difficult problems. Okay, sometimes it doesn't matter, but many times it does matter. So one of the starting points is, try to let u be something that gets simplified when you differentiate it. Okay, that's one strategy, but that doesn't work all the time either. So the way you get good at these problems is, obviously do a lot of them and you make the choices and you see what happens. Okay, and obviously we want to go from a complicated situation to a simple situation, rather than a complicated situation to an even more complicated situation. Okay, folks, everybody, I'm a little bit sad now. The tutorial is almost over. I told myself I wasn't going to cry, but I think there's something in my eye. Look, it's been great spending term 1 with you. And I know it's been really difficult for some of you with borders closed and travel not allowed and COVID-19 going on, coronavirus, all that sort of stuff. But I just wanted to say thanks to everybody for just making this tutorial lots of fun. And how many of you are doing math 1, 2, 3, 1 next term? Are you taking math 1, 2, 3, 1? next term? Okay, so good luck with that. I might see you there. Math 1231 is similar to this course. It has algebra and calculus. A lot of students tell me that in 1131, the algebra is easy and the calculus is more difficult. And a lot of students say it's the reverse in Math 1231. So the calculus is easier and the algebra is a bit harder. Okay, whatever you do, look, just good luck with your final exam, and I'll be thinking of you, and I'll be sending you. Get 100, get the marks that you want, whether that's a high distinction or a pass or a credit or something, and maybe I'll see you next term or in term 3. So good luck, and I'll sign off. And yeah, just enjoy the day. Thank you very much, everyone. Feel free to reach out if you need any help. Email me, whatever. All right, everyone. I will see you